Toss 3 fair coins and write down what happens. Heads, tails, heads, tails, 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 heads, heads, heads. There are 8 possible patterns in all, and each is a little story of ups and downs. Now suppose you only care about one thing. How many heads came up? Suddenly each messy pattern becomes a single clean number. 0, 1, 2, or 3. That act, turning a complicated outcome into a number, is the heart of what we're about to build. That number is called a random variable. And to describe it fully, we'll meet two partners. The probability mass function, which lists the chance of each value, and the cumulative distribution function, which adds those chances up. Let's build both from the ground up. Let's pin down the vocabulary first. A random experiment is anything with an uncertain result. Tossing coins, rolling dice. The set of every possible outcome is the sample space, written with a capital omega. And a random variable is a machine. Feed it an outcome from omega, and it hands you back a real number. We usually name it with a capital X. Here it is as a picture. On the left, 4 outcomes from omega. On the right, a number line, the real numbers. The random variable X draws an arrow from each outcome to the number it lands on. TTT has no heads, so it maps to 0. HTT has 1 head, mapping to 1. HTH has 2 heads, so 2. And HHH, all heads, lands on 3. Every messy outcome is now just a point on the line. Random variables come in 2 flavors, and the difference decides every tool we use. A discrete random variable takes values you can list. A countable set, like 0, 1, 2, 3, or all the whole numbers. A continuous random variable, by contrast, fills a whole interval of the real line, like any height between 1 and 2 meters. There's no gap between neighboring values. For this lesson, we live entirely in the discrete world. Variables whose values we can list, one by one. That's exactly where the probability mass function feels most at home. So for a discrete random variable, what do we actually want to know? The chance of each value it can take. That list of chances is the probability mass function, and it's written with a lowercase p. Read it out loud. P of x is the probability that x equals the value x. Feed in a value, and it returns how likely that value is. A lookup table of probabilities. Not every list of numbers is a legal probability mass function. 2 rules must hold. The first is non-negativity. Every probability is 0 or more. You can't have a negative chance of anything. The second is that the total probability is exactly 1. Sum the chances over every value the variable can take, and they must add up to a perfect one, because something is certain to happen. Picture that second rule as bars. Stack every probability on top of the last, and the tower must reach a height of exactly 1. No taller, no shorter. Keep that image. We'll return to it again and again. Let's build a real probability mass function you can feel. Roll 2 fair dice and add the faces. The sum x can be anything from 2 up to 12, but those values are far from equally likely. There are 36 equally likely rolls. A sum of 2 happens only one way, 1 and 1, but a sum of 7 happens 6 ways, so it's the most likely of all. Count the ways for each sum and divide by 36. And here is the picture. The probability mass function of the dice sum. 1 bar per value, each as tall as its probability. See how it climbs to a peak at 7, then falls away symmetrically. That triangular shape is the signature of adding to dice. The tallest bar sits at 7, with probability 6 over 36. That's 1 in 6. And if you added the heights of all 11 bars, they'd sum to exactly 1, just as our rule demands. The mass function answers what's the chance of exactly this value, but often we want the chance of this value or anything below it. That's the cumulative distribution function, written with a capital F. For a discrete variable, f of x is just the running total of the mass function. Add up every p up to and including x. Two features follow. It never decreases, and it climbs from 0 on the far left to 1 on the far right. Because the mass sits at separate points, the running total jumps at each value and stays flat in between. So a discrete CDF is a staircase. Let's watch it grow for the 3-coin variable. Below 0 heads is impossible, so f starts flat at 0. At 0, it jumps up by 1/8. At 1, it jumps again to 4/8, a half. At 2, it reaches 7/8. And at 3, the last jump carries it all the way to 1, where it stays forever after. The jump at each value is exactly the mass there. So the mass function and the running total carry the same information, one told point by point, the other accumulated. That link is the key to everything that follows. Time to put it all together. A discrete variable x takes the values 0, 1, 2, 3, with probabilities 0.1, 0.3, 0.4, and 0.2. We want its CDF and two probabilities from it. First, always check it's a legal mass function. Every value is positive, and 0.1 plus 0.3 plus 0.4 plus 0.2 is exactly 1. It passes both rules. Now build the CDF by accumulating. F at 0 is just 0.1. F at 1 adds the next mass. 0.1 plus 0.3 is 0.4. F at 2 adds 0.4 more, reaching 0.8. And F at 3 adds the last 0.2, landing on 1 exactly. With the CDF in hand, the questions are easy. The chance x is at most 2 is just f at 2. That's 0.8. Read straight off the table. For the second one, the chance x is more than 1 but at most 3. We subtract. It's f at 3 minus f at 1. That is 1.0 minus 0.4, which gives 0.6. Notice the strict greater than 1 means we subtract f at 1 itself. Let's return to our 3-coin variable and handle the trickier events, the ones with greater than or equal. Recall its masses are 1, 3, 3, 1 over 8, and its running totals are 1/8, a half, 7/8, and 1. First, the chance of at least 2 heads. At least 2 is the opposite of fewer than 2. So it's 1 minus the chance x is below 2. And the chance x is below 2. The left limit f of 2 minus is the mass at 0 plus the mass at 1. 1/8 plus 3/8, a half. So the chance of at least 2 heads is 1 minus a half. And you can check it directly. The mass at 2 plus the mass at 3 is 3/8 plus 1/8, which is also a half. The two routes agree. Last, the chance x is more than 0, but at most 2. For that interval, we take f at 2 minus f at 0, 7/8 minus 1/8, which is 6/8 or 3/4. As a check, that's the mass at 1 plus the mass at 2, 3/8 plus 3/8, 3/4 again. Your turn. A variable x takes the values 1, 2, 3, 4 with probabilities 0.2, 0.5, 0.2, and 0.1. Build its CDF, then find the chance x is at most 2 and the chance x is more than 2 but at most 4. Pause now and try it. I'll wait. Here's the walkthrough. First, check the masses sum to 1. 0.2 plus 0.5 plus 0.2 plus 0.1 is 1. Good. Now accumulate for the CDF. 0.2, then 0.7, then 0.9, then 1.0. The chance x is at most 2 is f at 2.7. And the chance x is more than 2 but at most 4 is f at 4 minus f at 2. 1.0 minus 0.7, which is 0.3. If you got 0.7 and 0.3, you've genuinely got this. Trap 1. There's no such thing as the probability of x on its own. Probability is always of an event. X equals 2, x at most 1, x between 1 and 3. Always name the event. Trap 2. Never trust a mass function without checking it sums to 1. If the probabilities don't total 1 or any is negative, it simply isn't a valid PMF. Trap 3. The CDF is defined with less than or equal, not strict less than. For a discrete variable, that difference matters exactly at the points carrying mass. Trap 4. The subtle one. Greater than a uses f of a, but at least a uses the left limit f of a minus. Mix them up at a point with mass, and your answer will be off by exactly that mass. Let's lock it all in. A random variable turns each outcome into a number, x from omega to the reals. Its probability mass function lists the chance of each value. Every mass is non-negative, and together they sum to 1. The cumulative distribution function is the running total. F of x, the chance x is at most x, a staircase climbing from 0 to 1, and interval probabilities come straight from the CDF by subtraction. Master these 4 lines, and discrete distributions will hold no surprises.